我们对解决青藏铁路冻土地区筑路技术难题的这个
Our guideline for building the Qinghai Tibet Railway on permafrost is this: to cool the soil of the railway bed and to reduce the amount of heat going into the ground. This makes the permafrost stable and stops the railway from sinking in summer.
It sounds easy enough, but keeping a 550-kilometer strip of land frozen during the Tibetan summer, when temperatures can reach 10 degrees Celsius above freezing point, is a monumental challenge. The first defense against the heat is building huge embankments for the track. There are 1,000 kilometers of embankments on the Qinghai Tibet Railway. The higher they are, the more they insulate the permafrost in summer. But they're more than just piles of rock and soil. Purpose-designed insulation panels make up one layer, but the most critical section is what's at the bottom of the embankment. A bed of crushed rocks, called plate stones, allows air to circulate between the railway bed and the permafrost.
The theory is that the spaces between the rocks are all connected, and it works like one seamless unit.
In summer, hot air rises and cooler air is trapped in the gaps between the stones, keeping the ground cool. The rock base is an effective low-tech solution, but it won't work for all unstable ground along the Qinghai Tibet Railway. To keep more volatile permafrost cool, the engineering team found inspiration in the people who have been living in this land for thousands of years. To survive the constant bending and buckling of the ground, houses built on the plateau have simple but ingenious foundations.
This is a concrete ventilation pipe foundation. You can see the ventilation pipes all lined up. We could see something going on here. Look at the middle part of the house. It's not distorted at all, but at the end, it's cracked.
The railway engineers noticed that if foundation pipes on permafrost are ever blocked, the walls crack. The air gap insulates the ground from heat generated inside the building. As long as the pipes are clear, the permafrost does not melt and the house remains stable. Adopting the same time-tested strategy, the engineers installed ventilation pipes in the railway embankments as an effective and cheap way of keeping the permafrost cold. But for even more fragile zones, Professor Zhang and the railway's chief engineer, Zhao She-yun, need a more high-tech plan.
We call this a heat pipe. These are heat radiation fins. So how does this device work?
The heat pipe is filled with liquid ammonia. It works like a refrigerator.
The air temperature can be over 10 or 20 degrees Celsius below zero. The ground temperature is only a few degrees below zero, and there is a temperature difference. The ground is warmer.
The warm soil turns the liquid ammonia at the bottom of the pipe into gas, and it rises inside the pipe. As the gas passes the radiation fins, the heat is released, and the ammonia cools and condenses back into liquid, then returns to the bottom of the pipe.
The heat pipe radiates the heat and cools the ground.
The heat pipes need no power supply. They're used on 32 kilometers of the line. But some icy ground is so unstable, no amount of cooling will keep it solid. You simply cannot build a railway bed on terrain like this. Tasked with the challenge to complete the line to Lhasa, the engineers have no choice but to come up with another plan. The new railway, stretching into China's far southwestern territory, Tibet, must cross vast stretches of extremely unstable permafrost and watery ground, which cannot hold the weight of railway embankments. The designers and engineers need a whole new plan to lay the track.
In some areas, we cannot guarantee the stability of railway beds built on permafrost, so we decided to avoid the permafrost altogether and build bridges over the top of it.
Without bridges, the ambitious plan to lay a railway across the Qinghai-Tibet Plateau would be impossible. Some cross rivers and ravines, but most bridges stand on flat land. This is the most unstable permafrost, which would collapse under heavy rail embankments. There are 675 bridges on the railway crossing the Qinghai-Tibet Plateau. The longest land bridge on the line runs almost 12 kilometers. But building bridges in constantly thawing and freezing permafrost raises a whole new set of problems. It all comes down to the concrete pylons. The engineers have to work out a precise way of pouring concrete into permafrost.
It depends on how long it takes the ground temperature to return to its original state. When we make the concrete pylon, it's frozen in with the permafrost, and that's what gives the pylon its load-bearing capacity.
The challenge for Professor Zhang and his team is how to insert concrete pylons into highly unstable permafrost without melting the icy soil. The first step is to drill the holes when it's cold, and the holes are dug dry. Normal drills use water as a lubricant, but water melts the underground ice. All pylons in permafrost are sunk deep to 20 meters below the surface. Installing the metal formwork quickly is critical. The whole process depends on minimizing the time the underground ice is exposed to warmer air. Then the concrete is fast poured. Concrete is the crucial ingredient of modern construction, as it is for the Qinghai-Tibet Railway. Using specific formulas, all concrete in the hundreds of thousands of pylons is specially mixed for the harsh Tibetan conditions.
We've used concrete that works in low temperatures. It sets quickly, it resists corrosion, and is very durable.
The most important factor in pouring the pylons is the temperature of the wet concrete. Cooled to just 5 degrees above the melting point of ice, the concrete quickly sets and freezes to the same temperature as the permafrost. It becomes part of it. Even when the upper layers of the permafrost melt and sink in summer, the deep ends of the pylons remain frozen in and maintain their load-bearing capacity.